Okay, so same directions, you guys. Find the interval of convergence and the radius of convergence of the sum n equals 0 to infinity, negative 1 to n, x minus 3 to the n, divided by 2, n plus 1. Okay. Well, nothing new as far as how we start. Find the absolute value of an plus 1 divided by an. So what does that look like? Go ahead and put in an n plus 1 wherever you see an n in this formula right here. That is what we're calling an. Okay, then x minus 3 to the n plus 1. So negative 1 to the n plus 1, x minus 3 to the n plus 1, that's what goes on top. And then, okay, if you plug in an n plus 1 there, let's get it all done now. That becomes 2n plus 2 plus another one, 2n plus 3. Okay, and then an, in this case, flip and multiply. So it would be, what, 2n plus 1 on top? And then negative 1 to the n, x minus 3 to just the n power. All of that inside absolute values. That's supposed to be a time symbol right there. Okay, so what do you want to do right away? What do you want to get rid of right away? The negative 1 to the powers, you can delete them, take the absolute value of them, however you think of it, but they're gone. And what else? Question? Oh, just stretching. Let's see. I will put the 2n plus 1 here. I'm going to write one big fraction. 2n plus 1, and then 2n plus 1. Notice if I write, or 2n plus 3, if I write one big fraction, I've got to put parentheses around the 2n plus 1 and the 2n plus 3. Then I'm going to put the powers of x minus 3 right next to each other. So I'm just rearranging the multiplication in the numerator and denominator, like that. And I suppose you could simplify the x minus 3 to the power, whatever power, in this step if you had wanted to. You could have done that, I mean to say. Okay, so I got rid of the negative 1 to the powers in the numerator and denominator. And then how does x minus 3 to the n plus 1 over x minus 3 to the n simplify? Just left with x minus 3. So I'm going to go a step further. I'm going to bring out the 2n plus 1 over 2n plus 3 outside the absolute value. And then I'm left inside the absolute value. I'm left with just x minus 3. Does everybody believe that? Okay, what does that converge to? As n, forget about x for now. As n goes to infinity, what does this thing converge to? Yeah, so let me get a wider view here. So this guy, using the arrow notation, converges to, well, okay, the 2n plus 1 over 2n plus 3 converges to 2 over 2, right? Which is 1 times the absolute value of x minus 3. Does everybody see what I did there? That's really, that arrow right there is really code for saying the limit of this guy as n goes to infinity, we're saying that's equal to x, absolute value of x minus 3.
Is the arrow shorthand common?
Yes.
Okay.
Yep. Very common notation, but it is dangerous because students, and this is just the way of things, you're not good with notation when you first learn about it. So if you only want to use one notation, use LIM, and you would just change it. The thing before the arrow would be the limit as n goes to infinity of this. And then equals absolute value x minus 3. It's a dangerous notation, but it's worthwhile because it saves a lot of writing. And then what do we need for convergence? Now we start talking about x. What do we need for the original series to converge? We need this limit to be what? To be less than 1. So we need, by ratio test, or now let me just make that statement, and then I'll say by ratio test later on. So the absolute value of x minus 3 Yeah, you know what? I can't think of another place to put it, so I will say that first. By ratio test, the series converges when. So that's a nice way to say it. And you can say it however you want as long as you use the words ratio test at some point, because that's what validates what we're doing. And then proofread it and make sure you have everything you want in there. By ratio test, the series converges when the absolute value of x minus 3 is less than 1. This is what gives us our interval, you guys, our interval of convergence. All right, so how do we drop the absolute values? What does x minus 3 have to be between? X minus 3 has to be between -1 and 1. And then to get x by itself in the middle, just add 3 everywhere. What do you get? What? Oh, wait, add 3. So this is what we're doing algebraically. To get rid of this 3 right here, we have to compensate by adding 3 here and here. So that puts x between what two numbers? 2 and 4. And that's mostly your interval of convergence, but guess what you have to do? You have to check the endpoints. So let's do that. So I'll check for endpoint convergence. Let's let x equal 2. Okay, and then what does the original series become when x is equal to 2? The sum n equals 0 to infinity, -1 to the n. Okay, so you plug, everybody look up. Everybody look up. You plug 2 in there. What does that make? -1 to the, oh, that's interesting. -1 to the n times -1 to the n on top. Oh, whoops, that's a pretty bad division bar. Divide by 2n plus 1. Okay, but wait a minute. What does that simplify to be? That's -1 to the n squared on top. Is that going to be positive or negative? Or is it going to change? What do you think? So I'm trying to determine how this that's a bad color to use. Let's use green. How does this numerator simplify? -1 to the n times itself? It's just 1. It's a squared number. -1 to the n squared is 1. Right? If you don't believe me, try a few n's. Try an odd n, try an even n. It's going to be 1. So you get the sum, n equals 0 to infinity, of 1 over 2n plus 1. And then you got to ask yourself the question, does that converge? And what do you guess? If you had to guess, what would you say? I would say no, too. This isn't that far. This 1 over 2n plus 1 isn't that far away from 1 over n, which we know the sum of 1 over n diverges. But you'd actually have to use the limit comparison test on this, I think. I don't think you could get the comparison test to work. I'm going to leave that to you guys, but I'm going to say this diverges. And then I'll say to you guys, use LCT. Okay, so it diverges, which means we're not going to include, what was the endpoint? We're not going to include 2. Do not include. Do not include. In your interval of convergence, in I for interval of convergence. But what about 4? So we checked 2, now we need to check 4. So I need to scroll down, unfortunately. So now let's check x equals 4. And oops, I need to scroll back up. Plug that into the original series. And then what do you get? -1 to the n. It was 0 to infinity, -1 to the n, times just 1 on top, right? or 1 to the n, which is just 1. 4 minus 3 is 1. So just 1 to the n, which is just 1, over, what was it, 2n plus 1? Yeah. Okay, is that guy going to converge? Converges by AST. Now, I'm going to make you guys do this for practice. Converges by AST. But it is something you should be able to do within the broader, within this entire broad problem. This is one aspect you should be able to fill in the details in. So on both of these, proof left to student. Proof left to student. So on both of these, right, you should be able to prove that. So and that one as well. So what about x equals 4? That's going to be included in our interval of convergence. So now we can state what I is. I does go from 2 to 4. What kind of symbol do I use around the 2? It's not included, so I use a parenthesis, one of them. And then around the 4? Bracket. In other words, you can include 4 in the domain of that infinite power series, because you can think of that infinite power series as a function of x. And then what's the radius of that thing? Yeah, remember, you get the radius by taking 4 minus 2, which is 2, divided by 2, which is 1. See if I can get this whole thing in view. Here it all is. So our answers are here.